We'll start with just a few housekeeping items. There will be time for questions at the end, so please write them in the questions box of your GoTo control panel during the presentation. If there isn't time to answer all the questions, then please reach out to me directly. I'll leave my email address at the end. This presentation is being recorded and will be available to watch at a later date. So thank you everyone for taking the time to join us today for this webinar and giving me the opportunity to share an overview of how WSP has utilized its Discrete Fracture Network software, FracMan, to better understand the subsurface potential for geothermal energy and carbon dioxide storage. My name is Ellie McInnes and I'm a technical director at WSP. I have over 20 years of experience as a geoscientist in the energy industry, working for several oil and gas operators and in the renewables sector. During this presentation, I will introduce you to WSP FracMan modeling software and how discrete fracture network models are useful in subsurface resource evaluations. We'll be focusing on the use of FracMan in geothermal and carbon dioxide storage examples. While some of the modeling methodology is similar for both use cases, there are also some key differences which highlights the versatility of FracMan. FracMan was developed in the 1980s, primarily for simulating the behavior of fractures in rock masses and predicting the flow of fluids through fractured media. FracMan has multi-industry functionality and can be applied to the engineering, environmental, hydrocarbon, mining, geothermal, CCS, nuclear, and hydrocarbon industries. WSP has developed 4 different versions to accommodate the different sector needs: nuclear, hydro, mining and geotechnical, and reservoir. Today we'll focus on the reservoir edition, which includes reservoir modeling, hydraulic fracture simulation for subsurface projects. So first of all, what is a discrete fracture network model? Well, it's a computational model used to simulate and analyze the geometry and properties of fractures within a geological formation to study the flow of fluids through fractured rocks. The key elements of a DFN model include the fractures, which are represented as individual entities with specific properties like length, orientation, aperture, and connectivity. These fractures can vary in size and location. The term discrete refers to the fact that fractures are modeled as distinct, separate entities rather than as a continuous medium. The fractures can interact with each other, forming a network. The connections and interactions between fractures can impact fluid flow, mechanical behavior, and other properties of the material. DFN models typically incorporate statistical distributions. Since the distribution of fractures in a rock form is not uniform, the DFN model generates fracture properties based on probabilistic distributions. DFNs can be used in flow modeling to understand how fluid moves through a fractured rock, mechanical modeling to assess how fractured materials deform under stress, and reservoir modeling, where fractures play a significant role in determining fluid flow. Overall, DFN models are critical tools for understanding complex fracture networks and for optimizing resource extraction and environmental management. So let's start with the application of FracMan DFN modeling to the evaluation of a hot sedimentary aquifer system in geothermal. Before we get on to our case study, I think it's useful to remind ourselves of the different types of geothermal systems and the technologies utilized. Firstly, on the different sources of heat. Hydrothermal geothermal involves reservoirs that are naturally heated by the Earth's internal heat. Typically, these are found in areas of volcanic activity or near tectonic plate boundaries, for example, in the Ring of Fire. Hot sedimentary aquifer systems, HSAs, utilize hot water stored in deep aquifers within sedimentary rock formations. These aquifers can be found in areas not necessarily associated with volcanic or tectonic activity. In today's example, we will look at a sandstone hot sedimentary aquifer near Denver. This example has the benefit of being in an area exploited for oil and gas production, and therefore has plenty of high-quality data available for the model. Geothermal produces baseload energy, and this sets it apart from wind and solar, which are intermittent. And when we look at the energy produced from geothermal today, we can see that there is 10 times more energy produced for direct heat and cooling than for power generation. The example we're looking at today is for power generation. So this presentation describes an example methodology and workflow for understanding a hot sedimentary aquifer prospect near Denver in the Rocky Mountains. Hot sedimentary aquifer geothermal systems exploit highly porous and permeable formations. And they utilize lower temperature water than in conventional hydrothermal geothermal systems, but this is balanced by the larger volumes of water that's accessible. The porosity and permeability is such that heat in both the in situ fluids and the solid rock can be extracted by combined matrix and fracture flow. The objectives of this FracMan DFN modeling project include optimizing horizontal well spacing, optimizing the injection and production rates, and understanding the thermal recovery of the reservoir over time. Having a robust understanding of these factors allows the geothermal operator to effectively plan and develop this resource. I would like to acknowledge my colleagues and several partners in this project, and if you'd like to learn more, please refer to the paper Evaluating the Geothermal Potential of Hot Sedimentary Aquifers Using a Hybrid Approach, published in 2023 by Cottrell et al. DFN modeling supports the understanding of fluid flow through naturally fractured systems. The efficiency of fluid flow through these rocks is highly dependent on the presence, orientation, and connectivity of fractures. The behavior of the injected water through the aquifer depends significantly on how fractures are connected. And DFNs allow for more accurate modeling of how water moves through the aquifer by simulating the network of fractures in 3D. By modeling the fracture system, DFNs can provide insights into the optimal locations for well placement and the expected flow paths of injected water. Well placement can be optimized in areas that have high permeability and thermal conductivity. DFNs allow for the prediction of thermal breakthrough, so the point when injected water reaches the well that is being used for extraction, and this helps in designing efficient operational schedules. DFN models help to predict long-term performance of a field by simulating the depletion of thermal energy from the aquifer over time. This is important for ensuring that the geothermal system is sustainable. DFN simulation can also help identify potential risks such as induced seismicity. The DFN modeling workflow starts with the data loading step, which provides the basis for import and assembly of the basic geological, geomechanical, and reservoir engineering data. It is typical for this step to include integration of well data, fracture logs, reservoir grids of properties, and photogrammetry data. Next is the visualization step, which provides the opportunity for visualization and validation of the available data. This often includes simulation of static fracture model data and comparison and validation with observed fracture intersections. The characterization step is the core effort in parameterizing the discrete fracture network. It routinely includes the configuration of the fracture set orientations and intensities, as well as calibration and description of the required dynamic fracture properties, including permeability, hydraulic aperture, and compressibility. The final step is the analysis. This is where the DFN description is employed for advanced quantitative analysis. For the current geothermal focus of this presentation, this step routinely relates to well design, injection and production strategies, stimulation requirements, recovery volumes, and storage capacity. The typical property descriptions required to build a coupled geothermal reservoir model in FracMan P-Flowtran system includes geometric, hydraulic, mechanical, and thermal properties. If you're unfamiliar with P-Flowtran, it is an open source simulator designed to model and simulate subsurface flow and transport processes. It is primarily used to model fluid flow, heat transport, and chemical reactions in porous media. In this case study example, there is a large quantity of data available, including well logs, cores, 3D seismic, geomechanical data, descriptions of facies and properties, as well as the presence of fractures and faults. Geomechanically, there are laboratory data describing rock stiffness, strength, and the in situ stress conditions. Reservoir engineering information is also available. Shown here is a simplified workflow from the field scale seismic and well fracture data to produce a geological DFN fracture model, and finally upscaling the DFN into a grid-based reservoir model description. These steps are important for upscaling DFN models to the more efficient continuum field descriptions required for geothermal reservoir flow simulation. The objective is to verify and extend this work to understand the level of reservoir performance in the case of thin layering, fracturing, and porosity and permeability of the targeted aquifer. So let's look at some of the simulation results. The injector well is at the top and the producer well at the bottom of each image. The figure on the left shows the predicted fluid pressure profiles around both the injector and the producer at various times after injection and production has commenced. The middle figure produces the corresponding evolution of the reservoir fluid temperatures during the injection and production process. The reservoir temperatures are largely unaffected after 30 days of injection and production. Only the toe of the injector shows a minor reduction in the temperature, and after approximately 3 years of operation, a volume of injected cooler water is established around the injector well. The cooler water volume continues to enlarge with time, and after 13 years, cool water extends between the two wells. After 16 years of operation, the cooled water volume is extremely well developed, so that the production well draws a mixture of original reservoir temperature water together with some injected fluids that have extracted some heat from the matrix. The figure on the right shows the tracer transport during injection and production, and this can be used to track injected fluid away from the injection well over time. So why are these results useful? Well, understanding the reservoir temperature and pressure evolution through time and during multiple simulations will help to constrain well planning and optimization. So this includes modeling the optimum well spacing for longevity of field and thermal recovery, and as a function of the well spacing. The results also help to assess the economic feasibility of the field. Through modeling the predicted harvested reservoir volume, HRV, and the thermal evolution of the reservoir through time, these results can be used to plan well and field developments. So in this DFN geothermal modeling case study, it's been demonstrated that DFN modeling supports the understanding of fluid flow through naturally fractured system. The fluid flow is highly dependent on the pressure, orientation, and connectivity of fractures. And by modeling the fracture system, DFNs can provide insight into the optimal locations for well placement and reservoir management through time. Hot sedimentary aquifers, which have also been exploited for oil and gas production, have the benefit of large quantities of high quality data which can be utilized to build robust DFN models. So next, we're going to explore how DFN modeling can be applied to CO2 storage. Geological CO2 storage is a process designed to reduce carbon dioxide emissions. It involves capturing CO2 and storing it safely underground. Most commonly, the CO2 is injected into depleted oil and gas reservoirs, which typically have large quantities of subsurface data available to use in the models of both the reservoir and the cap rock. Another example are deep saline aquifers. These are porous formations saturated with water, and there is often less subsurface data available. Understanding the geological heterogeneity, both stratigraphic and structural, is necessary for evaluating for the safe and effective subsurface storage. Understanding fracture networks in CO2 storage is important because they influence the flow of the CO2 and the interaction between the CO2 and the surrounding rock. By creating detailed representations of the fracture network, DFNs help us to understand how CO2 will migrate through the reservoir. One of the primary concerns in CO2 storage is ensuring that the captured CO2 remains securely stored in the geological formation without leakage to the surface. DFN models simulate the pathways that CO2 might take as it moves through the fractures in the reservoir. And this can help predict how CO2 will behave over time and whether it will remain trapped or potentially migrate along fractures through the cap rock or into groundwater supplies. The storage capacity of a reservoir depends not only on the volume of the rock, but also on the connectivity and porosity of the fractures. So DFN models can help to estimate how much CO2 can be safely injected and stored by simulating these interactions between the CO2 and the fractured network. The network's geometry and the permeability of the fractures directly affects the volume of CO2 that can be injected without causing undue pressure buildup or migration risks. Some of the key benefits of using DFN models in CO2 storage include the accurate prediction of how CO2 will behave within the fractured reservoir, and by understanding the fracture network, operators can design more secure and efficient storage strategies that reduce the risk of leakage, unintended migration of CO2, and microseismicity. So DFNs help to provide a more accurate CO2 storage estimate of a given reservoir. As with DFNs for the previous geothermal example, there is a range of subsurface data that's required to build a robust DFN in FracMan. This data covers a range of geometric, hydraulic, mechanical, and thermal properties. And this data is relevant for modeling both the reservoir and the cap rock. And it includes the fracture and matrix property data. And the availability of good data will depend somewhat on whether it's a saline aquifer or a depleted oil and gas field being used. As with the previous example, using the relevant data, we build a fully 3D model in FracMan of the fracture geometry, mechanical properties, storage, and permeability. We transform all 1D, 2D, and 3D geological, geotechnical, and well testing data into quantitative parameters to describe the fractured network. And the stochastic process allows multiple realizations via a Monte Carlo approach to constrain a range of outcomes. One of the most important aspects of CO2 fracture modeling is understanding the supercritical behavior of CO2 in the subsurface. DFN modeling helps assess the risks of leakage, the integrity of storage reservoirs, and the overall efficiency of CO2 storage. Supercritical CO2 is CO2 that's been pressurized and heated beyond its critical point. In this state, CO2 exhibits both liquid and gas-like properties. When CO2 is injected into a formation, it may encounter pre-existing fractures or faults. The injection process can cause changes in pore pressure and stress within the reservoir, potentially leading to fracture initiation or propagation. Some of the impacts on the reservoir and the cap rock can be stress redistribution, pore pressure increase, fracture propagation, fault rock interaction, reactivation of existing faults. So with this in mind, understanding the behavior of CO2 is essential for assessing the risks of leakage, understanding the storage integrity and overall efficiency of storage, ensuring well cap rock integrity, and well planning. From the example shown here, we can see the evolution of gas saturation on the left, gas pressure in the middle, and temperature on the right, taken at different intervals through time after injection. So at 50 hours, 1,000 hours, and 5,000 hours. The blue color indicates low values, and red indicates high values of each property. The wellbore can be seen as a thin blue line in the center of each image. The orientation, distribution, intensity, and interconnectedness of faults and fractures in the reservoir and cap rock are key factors. On the migration of gas through time and the associated changes in saturation, pressure, and temperature. A key concern during CO2 injection is fault reactivation. Some of the factors leading to fault reactivation include increased pressure and fault size, orientation, and pre-existing stress conditions. If the fault is critically stressed, even a small increase in pressure from CO2 injection could lead to reactivation. This can lead to an increased risk of CO2 leakage, microseismicity activity, and contamination of groundwater. So the DFN modeling workflow includes integration of data and construction of a reservoir scale DFN and fault model, simulation of well injection into the reservoir, which includes fluid pressure, plume, and hydraulic fracture simulation, calculation of fault reactivation conditions at various stages of injection, and the probabilistic assessment to help constrain uncertainties. So in conclusion, DFNs in geothermal and CO2 storage support improved reservoir characterization, enhanced site selection, improved dynamic risk assessment and mitigation, dynamic monitoring and long-term management, cost efficiency and planning, and understanding fault reactivation and microseismicity risk. And for geothermal cases specifically, DFN modeling supports improved fluid flow predictions, enhanced heat transfer simulation, and optimized resource utilization. And finally, for CO2 storage cases specifically, DFN support improved understanding of CO2 plume migration, optimization of injection strategies, and prediction of cap rock integrity and storage capacity. So thank you everyone for joining. If you'd like to learn more about FracMan and its capabilities for geothermal, CCS, oil and gas, nuclear, or infrastructure and mining, please reach out either to myself at ellie.mckinnis@wsp.com or fracman@wsp.com. And now for some questions from you. So I've got the first one here. What role does fracture network permeability play in the sustainability of geothermal systems? So fracture networks really play a critical role in the sustainability. The fractures can control the fluid flow and the heat transfer. So if you have a well fractured system, you can really get enhanced permeability and better heat flow and heat transport efficiency. If you've got a good fracture network, then you can also increase your long-term fluid supply. So having those large interconnected fracture systems can tap into a long-term consistent supply of hot fluids. Also, when we think about our flow pathways, so it's not just about the permeability of individual fractures, but about how they're connected within the reservoir. So really understanding your fracture system can help you to plan in the long term for how long a geothermal field will remain productive, and also kind of how you're best to plan the wells, the spacing between the wells, and your level of injection and production. So another one was, what are the limitations of DFN modeling in complex subsurface environments? So I guess it's like any model. It is a model. It's not a definitive answer. So in the examples that I showed, there was quite a lot of data available. So having good quality data will help you to build better models and understand the uncertainty. If you're in an area with restricted models, then obviously that will have an impact on the kind of quality of model that you can build. The subsurface is heterogeneous and complex, so whatever data we have will only give a small kind of view of what the subsurface is like. So there's a lot of assumptions that you do have to make, and that, I mean, that's the same with all models. There's also computational challenges. So, you know, some of these models are quite big. They take a while to run, and that's just a factor of the more data that you have, the higher complexity, and the more variations that you do, you'll have, you know, computational challenges with that. And I have a question. How do you incorporate interbed fractures which can form sub-inch to a few inches along? The number of these can overwhelm the number of normal sinusoidal identified fractures. So I guess this comes to scale. So you can build DFN models on a well scale, and we didn't look at that today, but some of my colleagues, that's what they focus on, is really on the well scale. Perhaps in the nuclear industry, that's more relevant. When you get to kind of the oil and gas or the geothermal field scale, it's really looking at the kind of the bigger scale structures. So I completely get your point. It's very scale dependent. I guess you have to ask what your question is, what you're trying to solve, and then from working out what it is that you're trying to solve, you can work out the best way to model it. You can't model everything at every scale. I guess you'd have to think about what you're looking for, and then tailor your workflow to that. And if it's something you want to chat to me about later, or I've got some colleagues who really specialize in this, then I'd be happy to take this offline. I have another question. How does FracMan DFN compare to Petrel DFNs? Would clients with Petrel expertise consider FracMan? That's a hard one for me personally to answer. I think FracMan is a very specialized DFN product. I haven't used Petrel DFN. It's been a while since I've worked in Petrel. So maybe again, that's if you want to contact me, we can have a chat about that later on, and we can do a comparison. Oh, what is the time frame for the development of a potential deep geothermal heating or energy resource? And have we implemented these for campus building, central plant, district energy projects? Yeah, so this is something that WSP does a lot of. We're involved in projects all over on this for the geothermal heating, and also on the power side. So quite happy, it doesn't say who asked this question, but quite happy to take this offline later if you want to contact me at ellie.mckinnis@wsp.com. I have one here. How do you measure information to quantify, validate the different permeability tensors of the model? I can't answer that one, but I'm quite happy to put you in touch with one of my colleagues that are deep users of FracMan. So please, I'll find out who asked that question and contact you afterwards. Is it feasible to apply DFN modeling to super hot geothermal systems or enhanced geothermal system? That is a really, really interesting question. I think we'd have to have a discussion with someone who's currently working in either of those species. I would think definitely the enhanced geothermal system and the super hot geothermal systems could both benefit from FracMan DFN analysis. I don't think we have, not sure what data sets we have on that, but yes, I know we have worked on the Forge project, or some of my colleagues have worked on the Forge project previously in Utah. So I think I have run out of time, but thank you very much. Really appreciate you all joining, and please reach out to me. I'm quite happy to take some of these questions offline and certainly put you in touch with my colleagues who have kind of the expertise in the different areas. So thanks very much, and I look forward to connecting with you all, and please reach out on LinkedIn as well. Okay, goodbye.